Section 14.5, curvature and normal vectors. Well, this is a little bit of a continuation from that was section 14.2, I believe, in which we found the tangential, or actually the unit tangent vector, and we already talked about it. So we found derivatives of vector valued functions. We divided by the magnitude of that vector valued function and to obtain an expression that would give us a unit tangent vector at a given value of t. Right now, so today we're going to look at something new, something called the curvature. Well, in this case, we're not just interested in only in the direction of the vector valued function, because it has a direction, and at a given point there's the tangent vector, some normal vector that we will discuss later. But we also want to know how fast a curve is turning, and that's determined by the curvature. Well, and just to give you a picture, for example, let's say between an ellipse and a circle, the curvature here is not that it's not going to be a big value. It's almost flat. However, at this point, the graph turns in a more steep way, if you will. I mean, the term steep is more for lines, And well, the curvature of a circle, it's always the same at every single point. It turns at the same rate, if we will, right? But now the thing is how we find that curvature. Well, if we were to do it the hard way, which is parameterizing a vector valued function so that it parameterizes arc length. Remember that long problem we did last time? Okay, so no, we're not going to do it that way. Fortunately, we have other ways to go about that problem, because I mean, even doing it the easy way is going to be one of these long problems, and it's more because of the algebra that we're going to use throughout every single problem. Well, so this curvature formula right here, which is given by the magnitude of the derivative of the tangential with respect s, that is, given that we have a vector valued function parameterizing arc length, which we're not going to do it that way. We're going to use another formula, which is the magnitude of the tangential divided by the magnitude of the derivative vector. So let's see, what about it? So how about finding the curvature for the curve r equals 5 sine theta, 5 cosine theta? Well, number one, just looking at this parametric equation or at this vector valued function, well, without doing any graph, what's this?
A circle.
It's a circle, right? We will argue that it's a circle, and whether it's parameterized sine, cosine, or cosine sine, what changes is the direction. In this case, we have sine in the x component and cosine in the y component. Then what we're going to have is a circle going clockwise towards the negative angles if we were looking in that perspective. Well, so number one, what do we do? So let's find, in this case, we need to find two pieces of information. The derivative of the tangential, which is the quotient between the vector derivative by and to its magnitude, and we also need to find the derivative of that magnitude. So I mean the magnitude of the derivative of the vector. So number one, let's start by finding the derivative of the vector valued function r prime of t, and that's the derivative of 5 sine, that's 5 cosine, and negative 5 sine t. Okay, so we need to find this derivative. Let's find then the magnitude, not the derivative, I mean the magnitude of the derivative That's the square root of the x component squared plus the y component squared. And this will be 25 cosine squared t plus 25 sine squared t. If we factor out a 25, we will be left with cosine squared t plus sine squared t. And we know this identity, we know cosine squared t plus sine squared t equals to what value? 1 times 25 is 25, and the square root of 25 is 5. Alright, so we need to find the tangential, that is the expression that will find tangent vectors for every single value of t. And we get this tangential by the quotient between the derivative vector, the derivative of the vector valued function, over its magnitude. And we actually got all these pieces of information, so in this case r prime, which is 5 cosine t minus 5 sine comma negative 5 sine t, and divide by the magnitude, and that magnitude we just found it in the previous step, that's 5. And in this case the tangential is, well, divide each component by the magnitude, that's going to give us 5 cosine t minus, oh wait, no, not 5, that's just cosine, negative 5, negative sine t. And we'll observe this vector valued function, that's cosine and sine. The coefficients are 1. This is a circle, and the radius of that circle would be the magnitude of the coefficients, right, which is 1. So that's a unit tangent vector valued function. Okay, so what else do we need? Okay, let's go back to our formula to find the curvature. And for the curvature, number one, we have to take the derivative of the expression that we just obtained, that is the derivative of the tangential, and divide that by the magnitude of the derivative of the vector valued function. This one we already have, that magnitude, that's 5 for us, but we need to find the derivative and the magnitude of the tangential. Well, so number one, let's start by finding the derivative of the tangential. So that's going to be negative sine t, negative cosine t. And finding its magnitude, well, this represents a unit circle. Ultimately, what do you think the magnitude of this should be? 1. Alright, but let's do the calculation. I'm going to show the calculation because for the next exercises, well, we are not going to have a clear view of what kind of vector value function we're dealing with. We're going to get something weird. For this one, it's pretty straightforward. It's a circle, but still, I'm going to do the calculation. So the magnitude of the derivative of the tangential will be the square root of negative sine t squared plus negative cosine t quantity squared. Well, again, surprise, this is sine squared plus cosine squared, and that's 1, and then the square root of 1 equals to 1. So we have everything that we need. So now we may go about finding the curvature, which is given by this kappa. That's actually the letter K from the Greek alphabet, but it looks like uppercase K, but it's actually very tiny. It's kind of weird, but it is. So, well, that's the magnitude of the derivative of the tangential divided by the magnitude of the derivative of the vector valued function. And well, in this case we have very simple results. In this case the derivative of the tangential happens to be 1, and the magnitude of the derivative of the vector valued function happens to be 5. And well, in this case, notice we're not getting any t's on. Technically, this k should be a function of t. Alright, because, well, in this case, we're just getting a numerical value, just a simple number, a constant. We're getting a constant because it's a circle. How's the curvature on a circle? Isn't it constant? Isn't it the same at every single point? So that's why we're getting a constant. It's not going to be the same for other cases. All right, there is an alternative formula to find the curvature. All right, and this alternative involves finding cross product of a couple of vectors and between two vectors, finding magnitudes, finding the cube of the magnitude. But again, one thing to keep in mind is that the cross product between two vectors is defined for vectors in 3 dimensions. That's because finding the cross product involves computing the determinant of a 3 by 3 matrix, which wouldn't be defined for vectors in 2 dimensions, because that would give us a determinant of 3 rows and 2 columns, and we can evaluate a determinant of a matrix that is not square. So in this case, what we do is make the third component a 0. That is, we add the k component, add a 0 times k, or if we have the component form, just add a 0. All right, like in this case, the previous example, we would have to use a 0. Okay, so for the second example, let's use the alternative way to get the curvature kappa of t to compute the curvature for the given function r of t equals to t negative 1/3 t cubed. All right. So what do we need in this case? Notice, let's look at the formula to find for the alternative. We need the velocity vector and we also need the acceleration vector. So what do we need to do to get those two vectors? First and second derivative of this vector valued function. That's correct. So that's the derivative of the velocity, which is no. That's r prime, which is the velocity vector, which is 2, 1, and that's negative 3/3, which is negative t squared. And then we need the second derivative, because the second derivative, which is the first derivative of the velocity, that'll be the acceleration. All right, and well, so that's going to be 0, 0, and negative 2t. All right, so we have the two vectors that we need to perform the cross product, the numerator part of the formula here. So, and well, we already have that v as well. So let's see, let's have a look at the cross product between the two vectors, and recall that this has to be done in the correct order. Recall that the cross product of two vectors is not commutative the way the dot product is. So let's see. So we're going to take the cross product between the velocity vector and the acceleration vector. So that's I, j, and k, and just write down the components of the vector. So, and actually, well, let me do it over here. So I might need space. So that's going to be 2, 1, negative t squared, 0, 0, negative 2t. All right, so we need to compute this determinant. Again, there's a couple of ways to compute this determinant. Number one, with the definition by cofactors and minors, or just duplicating the first two columns, which I think is shorter. And let's just multiply along the main diagonals. That's going to be I times 1 times negative 2t. That's going to give us negative 2t I I, and then j times negative t squared times 0, that's 0j. And k times 2 times 0, that's 0k. Minus the product of the secondary diagonals, and the secondary diagonals are the ones that we go in the backwards direction. J times 2 times negative 2t, that's going to give us negative 4t times j, and I times negative t squared times 0, well, that's going to be plus 0i, and k times 1 times 0, that's a 0k. Alright, so when combining this to this result, well, so we get 2t, because 2ti minus 4, that's 4t, wait, that should be, yeah, that's j, yeah, that's j. So actually this is, where am I getting negative? Okay, that's fine, negative 2t, I, and the j's, so that's a 4j, 4t in the direction of j, and 0 in the direction of k, which is negative 2t, 4t, and 0. So we got the cross product part. Alright? So what else do we need? So to find the curvature, we need to find the magnitude of that expression that we just obtained. Alright? So let's go ahead and do that right here. Magnitude of v crossed with a. And well, to find the magnitude of a vector, just take the square root of the sum of the components squared. That is negative 2t squared plus 4t squared. And make sure to square both the coefficient and the variable. And that's going to give us 4t squared plus 16t squared. And 0 squared, well, that's just 0. No need to write down that 0. And, well, that's going to give us 20, the square root of 20t squared, which can be reduced because the square root of 20, that's the same as factoring out 4 times 5. And the square root of 4 is 2. And what's the square root of t squared? Just t? Absolute value of t, because in this case, in the problem, it doesn't say anything about t. Assume something like assume t is only positive values. In this case, we're just giving the vector valued function, saying yes, we can have negative values. That doesn't mean going back in time. You know, those values of t are actually a reference, like 2 seconds ago, 5 seconds ago, or hours, depending on what this really models. So that's yes, 2 root of 5. So that's the magnitude. What do we have so far? Let's put a check on the formula. We got the numerator. Let's find the denominator. We don't have the magnitude of the derivative of the velocity vector, but check this out. We have the velocity vector here. So let's find the magnitude of the velocity vector, and that's going to be the square root of 2 squared plus 1 squared plus negative t quantity squared. Oh, careful, negative t squared squared. Alright, so that means we're going to have 2 squared, which is 4, plus 1, that's a 5, plus t to the 4th. Okay, so that's the magnitude, and we got the 2 pieces of information that we need. We got the magnitude of the cross product and the magnitude of the vector function.
We have to cube it.
And then now we're going to go back to the formula for kappa of t. That's going to be the magnitude of the acceleration vector divided by the magnitude of the velocity vector. All right, and well, the numerator we got, what is this? 2 absolute value of t root of 5 divided by, oh, this is cubed, by this radical 5 plus t squared, t to the 4th to the 3rd power. And well, this is essentially final answer, but we have a radical to the 3rd power, so all you might want to do here is 2 absolute value of t root of 5 over 5 plus t to the 4th to the 3/2. And well, let's compare results. In the previous example, we got a constant because we were looking at the curvature of a circle, and a circle has the same curvature at every single point. This is not a circle anymore. This is some kind of some different kind of path right here. That's something else. And well, we would expect to have different curvatures at different points. And well, that's why we have this expression in terms of t and not just a constant value. All right, let's see what's next. Now we're going to do another curvature problem. Find the curvature of the given vector valued function of the given path, and then they're going to ask us to find the curvature at the point 8, 2, 2. So now we're going to find how fast does the curve turn at this particular point. So first of all, we have to go through the painful process of finding derivatives. Well, that's not that bad, but the cross product is usually what takes a good minute to compute. So the velocity vector, which is the derivative, that's going to be 4t, comma t. Oh, wait a minute, that's 1, and that's t. Okay. We need the second derivative. That's the acceleration vector. The derivative of 4t, which is 4. The derivative of 1, which is 0. The derivative of t, which is 1. What else do we need here? Well, we need to find the cross product between the velocity vector and the acceleration vector in this order. Recall that if you do it the other way around, it's going to give you, well, essentially the same vector, but opposite sign for the components. So I, j, and k. Let's set it up. And we have the vectors 4t, 1t, 4, 0, 1, and just duplicate the first columns. And let's find the cross product. Well, product along the main diagonals, so that's I times 1, that's I. J times t times 4, that's plus 4, t times j, and 4 times 4, k times 4t times 0, well, that's a 0. I'm not going to write the 0 this time. And, well, subtract the products of the secondary diagonals. That's going to be j times 4t times 1, that's 4t times j, and I times t times 0, that's 0, and 4k times 1 times 4, that's a 4k. So let's simplify this term by term. I's with, well, that's the only I that we have, actually. So that's going to be I. And J's, actually, the J's cancel. Check how the J's cancel. And minus 4k, all right? Okay. But in this case, my advice is to, well, when you after computing the cross product between two vectors, because in some cases when one of the components is 0, you will see two terms. Just be careful and get them back to component form so you don't get confused about which components you're given or which components are missing. So that's 1, 0, negative 4. All right. So we got the cross product of the velocity and the acceleration vector. Let's find the magnitude of this vector. So that's the square root of 1 squared plus 0 squared plus 4 squared. And this should give us 1 squared, which is 1, plus 4 squared, which is 16. That's the square root of 17. All right, that's the first piece of information before we compute this in the formula. What else do we need? So there also, well, the formula for curvature also calls for the magnitude of the velocity vector. So, and we have the velocity vector right here. So let's find that out. Oh, just b. So that's square root of 4t quantity squared plus 1 squared plus t squared equals, so that's 16t squared plus t squared, that's 17t squared plus 1. And we got all the information, just put it in the formula for the curvature. Okay, so for now, this, what are we getting? Number one, we're getting an expression to calculate the curvature at any point. And that's going to be root of 17 over square root of 17t squared plus 1. The whole thing to the third power, that's the square root of 17 over 17t squared plus 1 to the 3/2. So this expression calculates the curvature, how fast the curve is turning at every single point. Now they're asking us for the curvature at a particular point, but wait a minute. This curvature expression, the input for this function is values of t. We're given an order triple. What do we need to know then before we can find that curvature? Any ideas? Because I mean, these are 3 values, and this formula calls for only 1 value.
We plug it into R.
Not plugging it into R, but sort of. So we would need, in this case, to find the value of t, or in other words, when is the particle at the point 8 to 2. All right, how do we do that? Well, in some cases it would be more straightforward. Oh, then find it at when t equals 2, when t equals 5, etc. But in this case, it's given in the form of the order triple. So this is what we're going to do. Okay, let me write down the order triple on top of the vector valued function. This corresponds to 8 to x. This corresponds to 2, and this corresponds to another 2. So number one, if we were to do it like the formal way, we would have to set a system of equations, 3 equations, and actually 1 unknown, and set a equals to 2t squared, 2 equals to t, and 2 equals to 1/2 t squared. In the first component and the third component cases, we would have to solve a quadratic equation, which is not the biggest quadratic equation in the world. It's a simple, what's it called? Square root property problem. However, in this case, go with the easiest. And the easiest is to say that t equals to... Do you have to solve anything for that one? Not really. So curvature at 8 to 2, that is when t equals to 2. All right, and just plug in 2 for the curvature formula. So that's k up 2, that's root of 17 over 17 times 2 squared plus 1 to the 3/2. Okay, let's compute this. So that's 2 squared, which is 4. 17 times 4, well, that's 17 plus times itself. Wait a minute, that's 54. And okay, 17 times 4, 50, 58. 58. Oh, 68. 68 and plus 1. Yes. And that's 69 to the 3/2. And we can leave it like this, unless otherwise specified well, so just approximate it to 2 or 3 decimals, but in this case, most of the times, we're going to leave it in exact form. So this is fine. All right. Okay, so what's next? All right, principal unit normal vector. Again, so curvature is going to tell us how fast a curve turns at a given point. But when a curve turns into one direction or the other, and that's what we want to know as well. So in this case, that information we're going to get it from the unit normal vector. And the unit normal vector, it's going to be the quotient between the derivative of the tangential divided by the magnitude of the derivative of the tangential. Of course, as long as the derivative of the tangential is not a 0. Well, this vector happens to be orthogonal to the tangent vector. That is, this means that the normal vector times the tangential vector should be equal to 0. That's the condition for orthogonality between two vectors. All right. So, well, what's the picture anyway? So we have a curve in one direction like this. Whoops. Okay. At a given point, whatever point, this point, we're going to have a tangent vector, the tangential in this case, and it's well, by the way, this has to be in this direction, right? Just so, because that's important. The tangential, it's always in the same direction as in the curve, you know? However, the normal vector, it's going to point towards the concave side of the curve, that is, in this direction, and it will be again orthogonal to the tangential vector, to the tangential. So that's the normal, and that's the tangential. Okay, we also have the second case, having the curve going in this direction. And choose any point, your favorite point, any point, and that's going to be a tangent vector. And again, notice the direction of the tangent vector is in the direction of the curve. And well, that's T, that's a big T. And at the same time, we're going to have this orthogonal vector, which happens to be the normal vector, and that's in the concave side of this of the curve. All right. Okay. Here is where a lot of algebra is coming up, and well, you know, check the exercise. I mean, it's only 2t plus t squared. What could look hard about it? Well, so number one, let's find the normal vector. Finding a normal vector involves finding the tangential, which involves finding the magnitude of the derivative of the vector, which is the quotient of the derivative vector. Well, let's see. Number one, okay, we want to find the normal vector, the normal unit vector, which is the derivative of the tangential over its magnitude. So let's start number one by finding the tangential first and then differentiating the tangential. But in order to get the tangential first, we need to get the r prime, because number one, we start at t, which is the derivative of the vector valued function divided by its magnitude. Okay, so number one, let's find r prime. So we got r prime is 2i. Well, actually, I'm gonna go to the component form, 2, 2t. All right, and we also need its magnitude. So, okay, yes, let me do it here. And this, I'm gonna move it here, and I'm gonna make it the same color. Okay. So, we also need the magnitude of the derivative, that's square root of 2 squared plus 2t quantity squared. So that's 4 plus 4t under the radical. So let's define the tangential. All right?
T squared.
T squared. Yes, 2t squared. 4t squared. So that's going to be the derivative of the vector valued function, which is 2 comma negative 2t, divided by this magnitude right here. And actually, you might want to simplify this this expression, because there's a common factor of 4, and we can take out a 2. Once we factor out the 4, take the square root of 4, which is 2.
It's 2t.
2t, which one? Oh yes, that's positive, right? I don't know why I have a negative on my notes, but anyway, that's fine. Okay, thank you. And that divided by 2 root of 1 plus t squared, which we can simplify, and I highly recommend that you simplify this, because these are gonna get really ugly in a second. Okay, so 2 over 2, that's gonna be 1 over the square root of 1 plus t squared, comma t over root of 1 plus t squared. Okay, so that's the tangential. And well, what else do we need? Okay, so we're ready to get started with information to obtain the normal unit vector. But well, what do we need to find the normal vector? We need the derivative of the tangential and divide it by the magnitude of the derivative of the tangential. So number one. So let's do one component at a time. So we need to differentiate. Let me use a different color. I'm going to differentiate component by component. So let's take the derivative with respect to t of the quantity. Well, I don't know. Maybe there's a typo on the original problem, because throughout my notes. So let's change this to negative. So because otherwise it's not going to work. Change this to negative, and well, that's positive. Should be negative and negative. Okay. So there was a typo on the original exercise just at the beginning. All right. So the derivative of 1 over the square root of 1 plus t squared. That's the same as saying the derivative of, because we cannot differentiate it just how it is. 1 plus t squared to the negative 1/2. All right. So to differentiate this function, we're going to need a chain rule with two layers in this case. So that's negative 1/2 times 1 plus t squared. And negative 1/2 minus 1, isn't that a negative 3/2? Times the derivative of 1 plus t squared. What's the derivative of that? 2t. Okay, let's reduce. Let's cancel the 2's. And this will be negative t over 1 plus t squared, the whole thing to the positive 3/2. And let's leave it like this for now. So that's the derivative of the first component. Let's look at the derivative of the second component. So in this case, we will differentiate negative t over the square root of 1 plus t squared. Well, number one, in this case, we will have to use a quotient rule, not the chain rule. Number one, let me rewrite this as 1 plus t squared to the 3/2. Oh, wait a minute, to the 1/2. And let's use the quotient rule in this case. And for the quotient rule, let me write down the formula just so you can see what am I doing here. So that's the derivative of u over v. That's u prime v minus v prime u, and the whole thing over the denominator squared. All right, that's the quotient rule. Let's see it in action with this function right here. All right, so u prime, that's negative 1. All right, so that's a negative 1 times the denominator without doing anything, 1 plus t squared to the 1/2 minus the derivative of the denominator, which requires a chain rule. That's unlit. Oh, I don't want this. And okay, so this requires a chain rule. That's a 1/2, and that's 1/2 times 1 plus t squared to the negative 3/2. Okay. Oh, actually, not the negative 3/2, to the negative 1/2, because it's the same in the denominator, times 2t. Alright, but that's just the derivative of the denominator. And for the quotient rule, we still need to multiply by u, which is the numerator itself, which is negative t. Alright? So, okay, just to check in, what did we do here? So that's u prime v minus v prime u. Okay? That's the quotient, the numerator part of the quotient rule. Okay? And let's divide everything by the denominator squared. That's 1 plus t squared to the 1/2 quantity squared, which will reduce really nicely. Alright? And this will be number 1. This is negative 1 plus t squared to the 1/2, and number 1, let's reduce this to lowest terms as possible. Cancel the 2, and negative times a negative becomes positive. And we also have the product of two t's right here, which will be t squared plus t squared, and that's 1 plus t squared to the 1/2, negative 1/2. The whole thing divided. How about cancel this half with this square? All right, that's just going to be 1 plus t squared. All right, so yes, we'd better simplify this, because we're just doing the part. We're still going to put this into the components, and we are going to divide the original vector value, well, the tangential, by the magnitude of the derivatives. And you don't want to square this whole thing. Do you want to do that? You want to do it. So let's simplify this derivative. Number 1, well, we have rational exponents. How about let's change this into radicals? So this will be negative square root of 1 plus t squared plus t squared. Isn't this 1 plus t squared to the negative 1/2? Number one, send it to the denominator with positive 1/2 power and then change it to radical form. Square root of 1 plus t squared. The whole thing divided by 1 plus t squared. Okay? And as a piece of advice here, you might want to write down that imaginary one, because in this case we will simplify the complex fraction. All right, that's one invisible one, and let me use a different color for that. And well, to simplify complex fractions, there's a couple of ways. Number one, you can work with the fractions in the numerator and then divide by the reciprocal of the denominator, which is fine. Or you can find a global greatest or a global least common denominator, but I think I'm going to do it the first way this time. Alright, so this is what I'm going to do to make it look nicer. So instead, how about I'm going to erase this, and instead of having this division, this crazy looking fraction, I'm going to put divided by 1 plus t squared. Alright? That way it doesn't look like a complex fraction. And well, to combine these two fractions together, we need to make these two the same denominator. So that's going to be negative root of 1 plus t squared over 1 and the least common denominator here will be to multiply by numerator and denominator by 1 plus t squared, 1 plus t squared. That divided by 1 plus t squared. We will take care of the division in the end. Now that we have the same fractions together, well, we have this radical being multiplied with itself. What happens when we multiply a radical by itself? The radical goes away, and we just get the expression inside of the radical. So that's going to be negative 1 plus t squared plus t squared from the numerator of the second term, and then the whole thing over the square root 1 plus t squared. And that times, or rather divided by 1 plus t squared. Alright? And then, well, let's change the division into a multiplication. What do we do to change the division into a multiplication? Multiply by the reciprocal. Have you ever heard of the Kfc rule? It doesn't have anything to do with chicken, actually. So Kfc. So keep, flip, and change. That is, keep the first term or the first factor, and that's negative. Well, let me actually distribute the negative 1 minus t squared plus t squared. Oh, cancellations. And keep the first fraction, flip the second fraction, and change the division into multiplication. That's the Kfc rule for fractions. And well, we're almost there. For the derivative, notice how negative t squared plus t squared cancel. And this is the same as saying to the 1/2. And when we multiply this together, that's negative 1 over 1 plus t to the 3/2. Do we all agree with this? Yes.
When you go back up to the derivative, shouldn't it be to the negative 3 over 2? Because when you bring it down for the chain rule, you bring the exponent minus 1.
In which step?
Like way up on.
Or way above?
I thought about that, but you can't do it because there's a plus
Where?
in that equation on the numerator.
Which is this part right here, or?
When you do the d low, so
Oh, okay, so let's repeat the quotient rule.
yeah, the derivative of v, I think.
Okay, the derivative of the v, which is, okay, the derivative, so that's 1/2 minus 1, that's negative 1/2.
Oh, okay. So there's no minus.
And you know what? Actually, when I did this step, actually by mistake I wrote the 3/2 and then I erased it because I think I was thinking the same as you were thinking. So that's the derivative simplified. Okay. Let's go back and write the derivative of the tangential. T prime of t. So that's going to be number 1, the derivative of the first component, which we got this expression right here. All right. Okay, let me zoom it out so you can see. So that's 1 plus t squared to the 3/2, comma, negative 1 plus t squared to the 3/2. All right.
So right above is it's negative 1 over 1 plus c squared.
Squared. Yes. T squared. Let me do the whole thing again. T squared to the 3/2. So that's only the derivative of the tangential. And to get an expression for the normal vector, we need to find the magnitude of this. All right? Because, okay, let me scroll up to, so that's, this we already got. We need to get this one. However,